Hello, welcome to the Sentic Labcast. My name is Xulang. I'm a research fellow in the Sentinec team. Today, my presentation topic is neurosymbolic sentiment analysis with dynamic word sense disambiguation. So first, let's introduce my motivations. Disambiguating polymerous words according to context is important for a variety of downstream tasks, especially for sentiment analysis. Words may appear in positive, negative, or neutral senses in different contexts and domains. For example, the word bearish is often used in a negative sense to describe the stock market in the financial domain. But in other domains, such as movie review, it is more likely to be used neutrally to describe hulking figures. A word may also have senses that carry opposite sentiment. For example, the word fine has the positive meaning of being delicate and refined, and also the negative meaning of monetary penalty. Existing sentiment analysis methods rely on neural networks to implicitly learn the word senses of ambiguous words. But this approach is not faithful or trustworthy because we cannot know whether the machine takes into account the correct word senses of ambiguous words when they're making the decisions. Or maybe they are just relying on some patterns nonsensical to humans. So to address this, we machine to disambiguate words by explicitly incorporating word sense disambiguation into downstream application. However, even though the WSD task, as we know it, is considered as solved, it is still a challenge to directly apply the existing WSD systems. This is because traditional WSD task is formulated as that given a sentence with the target words labeled, predict the correct word sense class of each target word. So this task setting limits its potential for downstream application. Specifically, due to the benchmark setup, existing WSD systems treats WSD as a sense classification problem or a gloss generation problem. So the output of traditional WSD systems are either sense label or gloss definition, which is difficult to directly integrate into downstream input. Furthermore, the target words must be predefined for WSD systems to disambiguate, making it difficult to apply them directly to downstream tasks. If every word in the input is disambiguated, it will lead to more time costs and higher possibility of error propagation. Lastly, since word senses are not discrete, the sense distinction of the benchmark dataset are not always reliable and might not contribute to the downstream application. Existing words have not explored the application of WSD to downstream tasks while also addressing these issues. Therefore, to reframe the WSD problem and integrate it into sentiment analysis, we propose a neurosymbolic framework that identifies the important ambiguous words in the input, and we paraphrase them into ones that cause less sentiment confusion to make predictions. In this way, our integration of WSD is interpretable and transparent because we can trace back which words are selected as targets and which substitute words are used to disambiguate them. Our framework is illustrated on the figure here. There are two models in our framework, sentiment analysis model and lexical substitution model. The Han model here is a interpretable attention model. It modifies the standard transformer attention so that the attention weight is a more reliable reflection of word saliency. The lexical substitution model is a pre-trained language model that we fine-tune beforehand to identify appropriate substitute word by using contrastive learning. So for sentiment analysis, we use the Han model to find words that contribute the most to the model's prediction. And from these words, we use the process shown on the figure on the right to find the words with the most diverse word senses and use them as the target words. We then use the lexical substitution model to paraphrase the target words and create the disambiguated input for sentiment analysis. Additionally, we want to further fine-tune the lexical substitution model to provide better substitutions that improve the accuracy of sentiment analysis. So we adapt a dynamic rewarding mechanism, which we will introduce in the next slide. So like I've mentioned, before we train our sentiment analysis framework, we first train our lexical substitution model by using contrastive learning on existing lexical substitution benchmark datasets. So we reformulated the input for contrastive learning as shown in the slide. The positive sample, or the ground truth, is the top ranking candidate, and the negative samples are the rest of the candidates. And the training objective is to close the Euclidean distance between the representations of the target word and the positive sample, while also pushing away the representation of negative samples. And for dynamic rewarding, as I've mentioned before, we want to keep fine-tuning the lexical substitution model so that the substitution it provides are more tailored for the sentiment analysis tasks. However, the problem is that we don't have gold standard truth for what is the best substitution in the sentiment analysis input. So we employ the dynamic rewarding mechanism where the top N candidates given by the lexical substitution model are all considered as ground truth to compute the losses. But each loss is weighted by the probability of the correct sentiment prediction after substituting the target word with the candidate. So if the replacement by a candidate leads to a higher chance of predicting the right sentiment, then the candidate will more likely get a higher rank by the lexical substitution model in the later iterations. So the pseudocode on the right showcase our framework in detail. The green box are the process to select target words to be disambiguated and use the trained lexical substitution model to replace them. And the new sentence is used for the final sentiment prediction. And the right box indicate the dynamic rewarding mechanism. For experiments, we first compare our framework with baselines on 3 datasets from different domains, including movie review, finance, and Twitter. Since we aim to improve a sentiment analysis classifier with explicit WSD, vanilla Roberta is considered as the most direct baseline because the encoder employed in our framework is Roberta. From the table, we can see that our framework achieves the best results on all 3 datasets. Most importantly, it outperforms Roberta, showing that our neurosymbolic approach to WSD can be adapted to improve PLM's performance on sentiment analysis. From the result, we can also make the hypothesis that the extent of improvement is dependent on domain types because sense ambiguity is more common in some domains than others. Next, we conduct an ablation study to prove the effectiveness of every component. From the results, we can validate our dynamic rewarding mechanism, our hypothesis about target words being salient and sense diverse, and our overall disambiguation framework. Next, we use visualization to demonstrate the interpretability of our framework. The figures shows the attention heat map before and after substitution. We can see that after substitution, the sentiment analysis model is able to put more attention on the sentiment-related words in the sentence. We also conduct an error analysis. So we can see that there are some error propagation from the lexical substitution model, but we can also see that by using our methods, we can trace back to what went wrong during the prediction process, and we can then perhaps employ targeted strategies to improve it in future work. To conclude, our paper proposed a neurosymbolic framework for sentiment analysis, which incorporates the disambiguation of word senses by identifying and paraphrasing ambiguous words in the input, which is realized by leveraging a pre-trained lexical substitution model. And then to fine-tune the lexical substitution model to provide better disambiguation substitutes for the sentiment analysis task with no ground truth word sense labels, we further adopt the dynamic rewarding mechanism to jointly train the sentiment analysis and lexical substitution models. That would be all. Thank you for listening to my presentation.